Hello everyone, I'm Sagar and I'm going to present a research paper on unsupervised cumulative domain adaptation for foggy scene optical flow. Optical flow or optic flow is the pattern of apparent motion of objects, surfaces and edges in a visual scene caused by relative motion between an observer and a scene, which you can see on the video on the right side. In simple terms, it's a method to track how objects move between consecutive frames in a video. It helps understand the direction and the speed of motion in a scene. Optical flow is good when it's clear, but it's not so great when it's foggy, because fog messes with how we see things like contrasts and brightness. Right now, methods try to make optical flow work in synthetic fog, but the fake fog isn't the same as real fog. This means they don't work well when there's a real fog. On this slide, we analyze the impact of fog on optical flow performance by studying how it varies with depth in the scene. As we can see from these images and optical flow examples at different depth range, the degradation caused by fog on both the image quality and the estimated flow accuracy become more severe as the depth increase. We quantify this by plotting the PSNR of foggy images and the endpoint error of optical flow against depth value. The trend clearly shows how at larger depth the PSNR drops significantly while the flow error rises rapidly. This indicates that fog is a depth-dependent, non-uniform degradation effect, with farther away objects being impacted more adversely compared to nearby region. Looking at the images and the flow visualization, we can observe that at larger depth, the image contrast is greatly diminished by atmospheric scattering effect of fog. Also, the motion boundary became blurred and distorted. This key analysis revealed that depth is an important physical factor influencing the optical flow performance under foggy conditions. To address the problem of optical flow estimation under real foggy scenes, unsupervised cumulative adaptation framework flow has been proposed. UCDA flow consists of two main modules. The first is called Depth Association Module, or DAMA, is designed to bridge the domain gap between clean scene and synthetic foggy scenes generated using atmospheric models. The second module is Correlational Alignment Motion Adaptation, or CAMA. CAMA focuses on bringing the gap between synthetic fog renderings and real foggy scenes. By combining DAMA and CAMA in a unified framework, UCDA flow can progressively transfer motion knowledge from clean data to handle real foggy scenes through a two-stage cumulative adaptation process. First, DAMA transfers from the clean source domain to synthetic fog domain. Then CAMA distills the synthetic fog knowledge into the real fog target domain. DAMA consists of the following key steps: depth association, geometric projection, motion adaptation. Depth association. DAMA utilizes depth as a key physical cue to associate clean image data with synthetic foggy data. It leverages the atmospheric scattering model to synthesize foggy image from clean RGB and depth inputs. Geometric projection. It enforces multi-view geometry constraint between depth and optical flow. Using camera poses, it projects the depth maps into optical flow space to obtain geometrically derived rigid flow. Motion adaptation. With the depth associated clean and synthetic foggy data, DAMA transfers motion knowledge across domains. It extracts motion features, computes cost volume, and decodes to estimate synthetic foggy flow. In essence, DAMA utilizes depth data to physically relate clean and foggy image domains, while geometrically constraining the optical flow estimation under fog degradation. This allows transferring motion knowledge from the clean domain to synthetic fog domain in a physical constrained manner. CAMA works by operating in the cost volume correlational space, which encodes pixel-wise similarities between frames. The steps are correlational, cost volume correlation. Cost volume store matching score correlation between pixel across frames. For both synthetic and real foggy image, cost volumes are constructed. Correlation distribution analysis. The distribution of correlation values in the cost volume are analyzed. It is observed that synthetic and real fog share a very similar correlation distribution. Correlation distribution alignment. The correlation distribution of synthetic and real fog are explicitly aligned. This is done by minimizing the KL divergence between their distributions. Self-supervised adaptation. The synthetic fog flow network predicts pseudo-labels for the real fog data. A self-supervised law enforces consistency between predicted real flow and pseudo-labels. By aligning the correlation distributions, CAMA transfer motion knowledge from the synthetic fog domain to the real-world target domain in a self-supervised manner using pseudo-labels. The correlation space acts as intermediate representation bridging synthetic and real domains, allowing knowledge transfer despite appearance shift. As you can see in this table, we have compared several methods with robust flow, U-flow, gyro flow, dense fog flow, and others, across different metric including endpoint error, F1all, and more. The results are divided into two data sets, LFKITTI and DFKITTI, representing light fog and dense fog scenario respectively. In the light fog dataset, UCDA flow outperform other methods with the endpoint error of 5.94 and F1all score of 34.11%. And on dense fog, UCDA flow achieves the lowest endpoint error of 6.29 and lowest F1all score of 36.25. Let's take a closer look at the visual comparison panel. Panel A shows the ground truth foggy images, while panel B2F displays the output of different methods, robust flow, dense flow, UF flow, gyro flow, and UCDA flow respectively. Here we can see the comparison of various model performance on three different images with the real fog and how accurately it defines the object and the optical flow object sharpness. After careful analysis, it's clear that UCDA flow stands out among all the model. It not only provides the sharpest image but also demonstrates superior object recognition compared to the others. These findings underscore the importance of choosing the right model for tasks involving real foggy conditions, with UCDA flow emerging as a promising option for its outstanding performance. First, let's examine the scenario without any adaptation. In this case, the flow distribution appears scattered and unfocused, indicating a lack of coherence in the prediction. Now let's shift our attention to the scenario where gamma plus gamma adaptation. Here we observe a significant improvement. The flow distribution is noticeably tighter and more concentrated, suggesting that the adaptation method have effectively enhanced the coherence and accuracy. The visual representation underscores the importance of cumulative adaptation technique in refining optical flow prediction, ultimately leading to more reliable and precise results. When the loss term is disabled, we observe a significant drop in performance. This highlights the crucial role of motion consistency in refining optical flow prediction, as its absence leads to less accurate and coherent results. Moving on to the correlation, alignment loss, we find that it plays a critical role, especially when combined with gamma loss. In this scenario, there is a notable gain over using gamma alone, indicating that correlation and alignment contribute significantly to improving the adaptation process. Additionally, other loss terms such as flow smoothness and rigid motion also contribute to the performance enhancement, further emphasizing their importance in refining optical flow prediction. In summary, the key takeaway from this analysis are cumulative adaptation progressively improve real fog performance by focusing the distribution further at each stage, and incorporating loss term in the adaptation process to achieve optimal results in challenging environment like foggy condition. Conclusion: unsupervised cumulative domain adaptation framework introduced UCDA flow, which addresses the challenging problem of optical flow estimation under real fog scenes. Bridging clean to synthetic fog gap, DAMA module was used to utilize the depth as a physical cue to associate clean and synthetic foggy data. And progressive knowledge transfer, two-stage cumulative adaptation approach, DAMA clean to synthetic fog domain, gamma synthetic to fog to real fog target domain. Thank you.